Welcome back to the online course on embedded system design, verification and test. By the name itself, we can say that there are three components in this particular course. One is your design, second one is verification and third one is test. I think by that time Dr. Arnav Sarkar might have covered the design issues of embedded system. I am Jatindra Kumar Deka. Now, we are going to discuss about the verification part, and finally, Dr. Santosh বিশ্বাস will discuss about the testing part of embedded system. So, now onward we are going to talk about the verification of embedded system. So, in general we are going to talk about the verification tools that is needed to verify some system design. Okay. Now, the first component for your verification is one logic by which you can specify the property of the system. So, in this particular course we are going to talk about the temporal logic. So, temporal logic will be used as a property specification language, and we are going to describe the properties of the system, and that property will be verified on the model that we are going to design, and model is nothing but the abstraction of the system that we are going to finally implement. So, if you look into the design cycle, the basic cycles or basic steps for your embedded system basically falls on those particular categories. One is a specification, depending on our requirement, depending on the user's need, we have to specify the system behavior. So, system behavior has to be specified in such a manner that it is going to satisfy all the requirement specification. Once the specification is ready, then from the specification we are going to have the design. So, once design is completed, then we will go for the implementation of the system. So, in case of embedded system, we are having two components, hardware as well as software. So, we are going to implement all the components, we will integrate them, and finally, we are going to get the system. Once system is ready, then we will go for a testing. Just to give you the assurance that whatever we have implemented, it is going to work correctly. And finally, it is installation and marketing, and later on the maintenance phase and upgradation will come into picture. So, these are the basic design cycle. Now, what is the challenges in this particular embedded system design? Generally, what will happen when we going to design a particular system, it may happen that design may not be perfect due to some of the reasons, and it going to lead some errors. Those errors are going to be treated as a bug of the system, and as a system designer team, we have to remove those particular bugs for the proper functioning of the system. So, it says that bugs reported at early phase of design incur less cost for debugging. Now, what will happen? Say in this particular design cycle, after implementation we are going for the testing. So, if during testing if some error is reported, then we have to fix those particular error. That means, again we have to start from the beginning, we have to look into the specification, whether specifications are correct or not, then we have to look for the again redesigning it, then again implement, then testing. So, one of the basic emphasis is that after design, if possible, we are going to capture the error that remains in the design phase, and once we can capture the error, then what will happen? Again we can go back to the design phase and we can redesign it before going to the implementation. So, we are going to capture the error at the early phase of design cycle. So, for that in the design cycle, we have incorporated one more step which is known as your verification. Okay. So, in that particular verification, we are going to check whatever design we are going to come up, that design is going to fulfill the requirement. So, design the abstract level, we are going to do it. So, for that verification part, what are the components required, what are the things needed, we are going to discuss in this particular series of lectures. So, there are several tools and techniques to go for the formal verification of a system design. So, in this particular course, we are going to look for a particular method which is known as your model checking. So, model checking is a property verification method in this particular method, what generally we used to do, we are going to check the properties that are going to be satisfied by the system that we have designed. So, that system design, or you can say that system or the model of the system that we are going to design. So, after the design phase, we are going to look for the property verification, or going to check whether all the specifications are going to made by our design or not. So, in model checking, basically we need 3 different components. One is called modeling. So, this is going to represent the entire system with the help of a model. We are having different formalism. For model checking, we need one particular formalism. We are going to discuss about that particular formalism. Then once the system is ready, then next step is we have to identify what are the properties that need to be satisfied by our system. We can say these are the specification of the system. So, we are going to have the model of our system, then we are going to have all the specification that is required to be satisfied by our system. Once we have these 2 components, then we need a verification method. We are going to apply this particular verification method to check whether specifications are correct in this particular model or not. So, basically these are the steps or requirement involved in the model checking technique. So, in pictorially we can see the system in this particular. First, we need to have our model. So, after having the specification and doing the modeling, then what will happen? We are going to have a system model. Now, how we are going to describe a system? In embedded system, we are having both the components, software as well as hardware. So, all the hardware components will be described with the help of some hardware description language. You may be knowing some of them as your Verilog or VHDL. So, implementation of the system will be described by those particular hardware description language if the components are hardware. We are having some software component. For that software component, generally we may use some high level language, maybe C, C++ or Java, or as per our requirement we can choose any programming language. So, hardware component and software component will be implemented with the help of respective programming languages. Then after that, we are going to abstract the model from those particular program. So, abstraction in some cases it may be automatic, or sometimes you have to do manually, or sometimes we have some semi automatic devices or methodologies to get the model of the system. And generally the model of the system is represented with the help of a finite state machine. Okay, it is a finite state model, because whatever may be the system, how complex it is, generally we are going to have a finite number of states, and we are having transition between those particular states. So, this behavior, that finite state model is going to give us the complete behavioral model of the system. So, once we get the model, then we are going to look for a specification. Apart from that, we are having some other formalism also to build a model. One is known as your state chart, which is proposed by Harrell in 1987. So, it is also extensively used to describe our model. So, after getting the complete specification of the system, instead of going for your software or hardware design, we can describe the model or behavior of the system with the help of state chart. Another formalism is there, which is called CSP, communicating sequential process. It was proposed by Ho in 1985. And another method we have CCS, calculus of communicating system. It was proposed by Milner in 1980. So, if we need, we may use those particular formalism also to get the model of the system. When the model is ready, then we have to see what are the properties that need to be satisfied that particular model. So, in that particular case, we are going to have the finite state model of the system. So, basically these are the different state a system can have, and these are the possible transition we are saying, and this is a complete state transition behavior of the system. So, we are going to have this particular model, and the specification have to be given in some specification language which is having a proper syntax, and those syntax has been given a proper semantics. So, here we are just giving some symbols over here, that box phi implies diamond psi. So, this is a one kind of language through which you can specify the properties. So, this finite state model and specification will be given to the verification tool, and in that particular course we are going to look model checking is a verification tool. Once we give this particular specification and finite state model to verification tool, then verification tool will give us a result as OK if the property holds in this particular model. Okay. So, this is one way you can look into it. So, if property is satisfied, then verification tool will give us OK. If the property is not satisfied in the model, then what will happen? It will give us an error trace. It says that if we go through this particular error trace, then if you follow this particular trace, then your property is not verified. It may happen that, say, we are having several transition part from this particular state. So, it gives something like that. If the property is not satisfied, say, in this particular transition, okay, then it will give us this particular error trace. That means, if we are moving from state in this particular part, then the given property is not satisfied. So, in that particular case, as a design team, what we can do? We can concentrate on those particular part to fix the bug. Once we fix the bug, then what will happen? Again, we repeat this particular process of verification. Finally, if it says OK, that means the given specification is correct. So, in this particular tool or method model checking, generally we use temporal logic to specify the properties of the system. So, in the previous slide, whatever we have written this statement as a specification, this is a kind of temporal logic formula. We are going to discuss or going to see what are the meaning of those particular symbols. So, in case of temporal logic, what will happen? It is going to capture the timing behavior of the system, because if it is a state transition system, say I am in a state S1, S0, then I am having a transition to S1, or maybe it can have transition to S2. From S1 we can go to S3, then what will happen? This is the transition behavior of the system. So, in that particular case, what will happen? If in time t0 the system is in your S0, then in time t1 it can go to state S1 or it can go to state S2, and once it comes to the state S1, then in the next clock cycle system can go to S2. So, this is the timing behavior of our system. So, temporal logic can capture this particular timing behavior, and when we are going to look into the timing nature of the time, it can be look into two different aspects. One is your linear and second one is branching. Also, time can be treated as your qualitative and quantitative, and we may have the discrete notion of time or continuous notion of time. So, in case of branching and linear, what will happen? In case of linear, we say that time progresses in one particular transition or one particular execution trace. But in case of branching time logic, what we consider that from a particular state, we are having several possibilities, system can transit to several possible behavior, and but at any particular instance of time, it will take only one next step. Okay. Just in case of this particular diagram, you just see, if we are in this particular state, then we are having three possible behavior of the system. So, time progresses in these three different directions, but at any particular instance of time, it is going to take only one next state behavior. It cannot go to all these three next state behavior. So, depending on the environment or the system variable, either it is going to take this particular part or it may take the other two parts. So, in this particular case, the timing or behavior of the timing is branching in nature. So, we are going to see all possible cases and we are going to region about the system in impossible direction. But in case of linear time, at particular instance of time, we are going to look for one direction only, one execution trace in one time direction only. So, at that time we may ignore the other two behaviors, but later on once we look the behavior in one direction, then we can go for the second direction. In linear time logic, we just look for one particular execution trace. But in case of branching time logic, we are going to look the entire system as a whole and we see the behavior in all possible directions. So, temporal logic is having two different notions, one is your linear time, second one is your branching time. It is qualitative versus quantitative. So, it says that something will happen in future, something will happen after some specific time. So, you can say the simple example generally we used to say in our network protocol, if we send a message, then eventually the sender should get the acknowledgement from the receiver. So, this is a property that need to be satisfied by the protocol in our network system. So, here says that if we send a message, then sender should eventually get the acknowledgement message, then only sender will be knowing that message has been delivered properly. So, if we are going to specify the property in that particular way, then we are going to say this is your qualitative in nature. We say that eventually or in future it should get the acknowledgement. But in quantitative nature, what will happen? We are going to specify the quantum of time. So, in that particular case, what we will say that if sender sends a message, then sender should get the acknowledgement after 5 units of time. So, here we are not saying eventually it should get the acknowledgement, but we are saying that after 5 time units. So, what we are saying? We are giving some quantitative measures. So, that means sender will wait for 5 time units, and within 5 time units if sender does not receive the acknowledgement, then what will happen? In most of the protocol we retransmit the packet again. So, these are the two ways can specify the timing behavior, one is your qualitative in nature, second one is your quantitative in nature. In our course we can discuss, we will see both the behaviors actually one after another. When we come for the quantitative one, that means we are saying that after 5 units of time or say after 10 units of time. So, this quantum of time can be a discrete in nature or it can be continuous in nature. So, in case of discrete time domain, what will happen? We are going to give discrete time units. So, after 1 time unit, after 2 time unit, after 5 time unit or maybe after 10 time unit. But in continuous time, generally we are going to look for the continuous timeline. So, it will be specified in real numbers. So, we can say that after 5.5 time units or say 5.5 seconds like that. But if we work in the digital domain, in most of the cases you will find that the time that we capture in our digital system is always controlled by a master clock and the nature of timing discrete in nature. So, our emphasis will be on the discrete time system. We may not give emphasis on the continuous time domain, because in continuous time domain system become very complex and the verification of property is even more complex. But when we work in the discrete domain, it is relatively easy. So, time behavior can again look into as a discrete in nature or continuous time. Now, in temporal logic, we are having a provision to capture the timing information. Okay. This is the addition part in the temporal logic. It is like your, I think in your classical logic you know about propositional logic, predicate logic or higher order predicate logic. In those particular logic we cannot capture the timing behavior, but temporal logic we can capture the timing behavior. So, in case of temporal logic, what is the truth values of a temporal logic formula? The truth values of a temporal logic formula always defined with respect to a model. So, if we are writing a temporal logic formula, simply you cannot say that it is true or it is false. the truth values of a temporal logic formula is always specific to a particular model. So, in simple example I can give in propositional logic, what I can write? I can say that P or not of Q. So, this is a formula in our propositional logics. So, in truth values of this propositional logic will be either true or false depending on the truth values of P and Q. Secondly, if I say that P or not of P, again it depends on the truth values of P, and we know that this is a tautology, this is always true. But in case of temporal logic formula, we cannot say that the formula is true or false, but always you have to give the meaning truth values of the temporal formula with respect to a model. Secondly, temporal logic formula is not statically true or false in a model. So, we cannot say that this given temporal formula is true in this particular model A or it is false in the model B, but it depends on the state behavior of the system or maybe transition behavior of the system. So, we are having two type of temporal logic formula, one we say that state formula and second one is your path formula. Okay. So, if path formula, if we are going to talk about a path formula, it says that the temporal logic formula is true in a particular part of the given model. And if we say that state formula, that means that temporal logic formula is true in a particular state of the given transition system. So, the model of a temporal logic contains several states and a formula can be true in some states and false in some others. So, truth values of the temporal logic formula is specific to a state if it is a state formula. So, for a given temporal formula in a given model, the formula may be true in some of the states and it will be false in some other states. Similarly, if it is a path formula, the formula will be true in some of the paths, but it may false in some other path. Okay. So, this is basically now I can give emphasis on that. Say if I am going to consider a particular model, state transition model, something like that. So, if I am giving a temporal logic formula and say this is the state S n, I can say that given temporal formula is whether true in S n or false in S n. I can just talk about the state. If it is a state formula, we cannot say that given temporal formula is true in this given model, it is not true. Similarly, if it is a path formula, we are going to say that whether the formula is true in a particular path or not. Okay. So, notion of the truth values of a temporal logic formula is defined on a state if it is a state formula, or it is defined on a path if it is a path formula. Now, what we can specify in our temporal logic? Very simple statement I am giving, say I am always happy. So, it talks about I am always happy. So, whether can I specify these things temporal logic? Yes, we are having construct to specify these things, or we can say that I will eventually be happy. Now, I may not be happy today, but in future or eventually I will be happy. Another one I will say that I will be happy until I do something wrong. Today I am happy and I will remain happy till I do something wrong, because if I do something wrong, then I may go to depression or I feel unhappy or I am happy. This is the current status. Okay. So, these are the things where we are capturing the timing behavior of our lifeline. So, such type of timing can be captured with the help of temporal logic. So, what we have in the temporal logic? Already I have mentioned that we are having propositional logic, we are having some propositional logic operator like disjunction or operation, conjunction or and operation, then if then, implication. Okay. These are just some basic operator that we have in our propositional logic, or we can have negation also, not. So, whatever logic operator we have in our logic family, all those operators can be used in our temporal logic. That means, two formulas can be conjuncted with the help of an operation, or we can use the disjunction also on two formulas to get another Finite formula. So, and I think you know the meaning of those particular operators. So, we are going to use the same meaning in temporal logic also. So, we are going to use the logic operators in our temporal logic also. Along with that, we are having some temporal operators. So, these are the addition operator that we are having in our temporal logic. So, all the logic operator as well as we are going to use the temporal operator also in temporal logic. Now, we are going to discuss about those particular temporal operators. What are the temporal operators that we have in our temporal logic? So, there are four basic temporal operators that we have, but we can look for some other operator also, but that can be again implemented with the help of those particular basic operators. So, what are the basic operators that we have in our temporal logic? Here, if you look the historical development of our temporal operators, it has given some symbols to represent this particular operator. One is your circle, diamond, box and U. So, these are the operators symbols that generally used in the temporal logic, but nowadays we are going to represent those particular operators with textual notation, and in case of textual notation, what are the alphabet we are using? It is X, F, G and U. X is nothing but it talks about the next step. This is X. F is basically future. Then globally is G and one is your until U. So, these are the four letters we use. So, basically if I say that x phi, phi is a temporal logic formula, x phi is also a temporal formula. It says that phi holds at next state. If I say that f phi, it says that phi eventually holds or phi eventually becomes true. G phi, it says that phi holds globally, and phi until psi, it says that phi holds until psi holds. That means, phi remains true until psi becomes true. Okay. So, these are the four temporal operators we are going to use in while going to specify or when going to capture the timing notion of our system. So, four operators basically we are having. One is your next, second one is future, then globally and until. So, now how we are going to get the truth values or how we are going to define it? It is going to define in a model. So, temporal formulas are interpreted over a model, okay, which is an infinite sequence of states. Okay, it is having infinite sequence of state, but we are saying be clear about it. We are talking about infinite sequence of states, but we are not talking about infinite states, because whatever system we are going to model, in reality we will say that all are having finite states, but that finite state, some of the state may repeat forever. Okay. So, we are going to get an infinite sequence of state. Simple example I can give, say in a model I can have such type of behavior. So, you just see that if I am going to have this particular execution trace, I am having 4 states only, but system can go to this particular part over and over again. So, we are going to get an infinite sequence of state. So, temporal formulas will be interpreted in the model where we are going to get some infinite sequence of state. So, how we are going to define it? Given a model M, so this is the model M and a temporal formula phi, okay, we define an inductive definition for the notion of phi holding at a position S j in M, and it is denoted by M S j model phi. That means, in the system M in the state S j phi is true, or you can say that M S j model phi. So, if we are using this particular Sj, that means we are going to talk about the state formula. Similarly, we can say that in the model M, in the part pi I, it models say psi. In that particular case, psi is a part formula, and truth values of the part formula is defined on a particular part pi I. So, this is the way we can always interpret that we are going to look for the truth values of a temporal formula in a model, and in the model we are going to look for an infinite sequence of states. So, again two issues are there, one is a state formula, second one is part formula. Truth values of the part state formula will be defined over a state, and truth values of a part formula will be defined over a part. So, this is the some state transition diagram. Okay. So, state can have this particular behavior, I can say something like that. So, we can talk for state formula, we can talk about a particular state say as a, okay, or I can talk about the truth values of a formula in a particular part say pi I. Okay. So, this is basically part formula which will be defined over this particular part, and this is a state formula which will be defined in a particular state. Truth values will be defined on this particular state. Now, what is the meaning of those particular operator? When I say that next operator or x operator. So, it says that x phi. What does it mean? That means, it says that if I am in a particular state, whether something holds in the next state or not. Okay. So, the truth values is defined like that. So, M S J, it models x phi, where x phi is a temporal formula, next phi. When we say that M S J whole x phi, if or provided if M S J plus 1 models phi. So, this is the next state. So, in this particular case you say this is my state S I S J, okay. This is the state S j plus 1. Okay. So, if we say that phi holds in this particular state S j plus 1, then according to this particular definition of next operator, we can say that x phi holds in the state S j. So, that is why I am saying that model M S j model x phi, or x phi is true in the state S j if we are having such type of behavior in our system. That means, in the next state j plus 1 phi is true, then in state S j we are going to say that x phi is true. This is the way we are going to define the truth values of a temporal formula which involve this particular next operator. So, this is a simple meaning of next operator. Similarly, the next operator is future or f phi. So, when we say that this particular formula f phi will be true in a particular state say S j. So, it says that in a model M in S j holds f phi, that means M S j model f phi, this is future phi, this is a temporal operator, provided or if and if we are going to get some k, here exists some k, where k is greater than equal to j, okay, and M S k models phi. Okay. So, we are going to have some k S k where phi holds, then we say that in a given state j S j f phi will true provided k is greater than equal to j. So, in this particular case I can say that this is my state S j and say this is my state say S k, and inside that in S k it phi is true, just I am labeling it phi, it indicates that in this particular state phi is true. Okay. So, in that particular case if I look into the S j, we will find that if I go through this particular execution trace, somewhere in future we are getting a state where phi is true. So, in that particular case I said that here in this particular state f phi is true. So, similarly, if I look into this as j plus 1, again we will find that f phi is true in j plus as j plus 1 also, because from this particular state if we go through this particular execution trace, in future I am going to have the state where phi is true. So, in this particular case also we can say that whatever state we are having before this S k in all the state f phi is true. So, this is the notion of the future. G phi globally, it says that whether globally phi is true or not. So, how we are going to define it? If we are going to look for one particular state, say S j in a model M, when we say that G phi holds in your model M in state S j, if provided for all k, where k is greater than equal to j, we are going to say that M S k models phi. So, in all state, wherever we go from this particular state, if everywhere k is phi is true, we say that G phi is true at that particular point. That means, you can say that phi is globally true. Now, in this particular case, say if this is my S j, if I say that phi is true over here, phi is true over here, phi is true over here. Okay. But now, can you say whether G phi is true at that particular point? It will be slightly difficult, because phi is true up to this particular point, but we do not know what is going to happen in future states, whether phi will remain true or not. So, in that particular case, I cannot say that G phi holds in this particular state, but if I am going to have another system, so, in this particular case, what will happen now, if this is the state say S 0 and say this is model M, whether in the model M in state S 0, whether it phi holds or not. So, in that particular case, what I can say that yes, phi holds in G phi holds or not. So, I can say that in state S 0, G phi holds, because wherever you go, which execution trace you take, in all the states in future phi is going to be true. So, in this particular model I can say that yes, M S 0 model G phi, but here it is slightly difficult to say, because I can have one state somewhere here, because I am talking about a continuity and say phi does not hold over here. So, in this particular case I cannot say that in S j G phi holds. So, in all possible states, if phi is true, then we say that globally phi is true, and it is true for all the states. Last operator is your until, psi until phi. So, what is the notion? It says that in the state S j of M is satisfied psi until phi, provided psi holds in a state and all the state previous to that particular state, if phi holds, psi holds, then we say that psi holds, psi until phi holds. So, here you just see it says that in this particular state psi until phi holds in S j, provided there exists some k where M S k models phi, and in all j where j is less than equal to k, M S j model psi. Okay. So, in that particular case we say that in the state S j psi until phi is true. Now, come to this particular point, say if I am going to say this is say phi holds over here, and say this is the state S k, and say this is your S j plus 1, S j plus 2 like that. So, if all those states say psi holds, then what we are going to say that from this particular state S j in this execution trace, we are going to get one state where phi holds in state S k, and all the previous states whatever we have encountered in all those particular states psi is true. Then in that particular case, we are going to say that in this particular state S j psi until phi holds or psi until phi true. So, something remains true until some property becomes true. So, this is the notion of until operator. So, in that particular case, if this is the scenario, then we are going to say that in that particular state psi until phi is true. So, these are the meaning of those particular temporal operators. What are the temporal operators we have discussed? Next state, future, globally and until, and these are defined in a model. So, this operator can come as a state formula or it can appear in a path formula. Here, when we are going to when we are going to look into the truth values, if it is a state formula, we are going to talk about the truth values in a particular state. If it is a path formula, then we are going to talk about this truth values of the formula in a particular path. But here the way we are defining, basically we are defining the truth values of the temporal operator in a state. Okay. So, these are the 4 basic operators that we have. Now, say whatever we have discussed or that operator, basically these are future in nature. So, we say this is future logic, because we are in a current state and from here we are going to reason about the system in the future. That means, how the system is going to behave in future. So, this is basically future logic. So, similarly, we are having the notion of past logic also. So, in past logic also we are going to have the corresponding operator with respect to the operator that we have in your future logic. So, in future logic we are having the next. So, in past logic we are going to get an operator previous. In future logic we are having the operator future. So, here we are going to have eventually in past. In future logic we are having global operator. So, in past logic we are going to have globally in past, and we have the until operator. So, in past logic we are going to have back to operator. So, if we are going to reason about a system from a current state and how the system is going to behave in future, then we are going to use the future temporal logic. But we are coming to a particular state, but if we want to know what was the behavior of the system in the past, then we have to use the past temporal logic. Basically, we have to use the operator that is available in the past temporal logic. So, this is basically similar to your future temporal logic. So, in case of future temporal logic, we are having a next state, but in case of past temporal logic, we are having the previous. Okay. So, in the temporal logic, we are saying that circle is given as a next state. So, if we write circle and inside that if we write the tilde, then it is going to say this is the previous. So, if this is the next operator, then with tilde we are going to get the previous operator. So, this is says that as j satisfied that previous phi as its previous state as j minus 1 satisfies phi, it is same. So, if I say that S j is a state and S j minus 1 in the previous state phi holds, then we say that in this particular state previous phi holds. Okay. So, this is the notion of the operator previous, which corresponds to your next operator in the future logic. Similarly, second one is your eventually in past. So, in future temporal logic, we have the future operator, which is given by a diamond. So, we are using the same diamond symbol and with the tilde inside it. Okay. So, this is the eventually in past. So, it is also same notions that we are having. If whether it satisfies eventually in past phi. So, if we are in a particular state say S j, then we are going to look for some previous state S k where phi holds, and we said that in this particular state S j eventually in past phi holds. Okay. So, this is corresponds to the future operator. Similarly, globally in past. So, that box is used for the global operator. So, box and inside that if we put the tilde symbol, then it is the globally in past. So, what basically the notion is same. If we are having this particular state say S j, if all the previous state, say we are starting, this is starting state, in all the previous states say phi holds, then we say that in this particular state S j globally phi holds. Okay. Similarly, we are going to have this particular back to. So, phi holds back to psi holds. So, that means, if in a particular state say phi holds and all the previous state phi holds, still we get a state where psi holds, then we say that phi back to psi holds in this particular state, if it is a state formula, or if it is a path formula, then we will say that in this particular path phi back to psi holds. Okay. So, these are the future operator. Now, I think I have also not mentioned properly in this particular case, in most of the cases you said I am talking about j is greater than equal to k, this is greater than equal to k. Okay. We are not simply writing this greater than, but we are writing greater than equal to k. Similarly, here also I am writing less than equal to k. So, this is basically in case of your past logic or future logic also, you will find that we are going to have that notion also, say less than equal to, here also greater than equal to k. So, in those particular case, it is having say greater than equal to k. So, we are talking about either greater than equal to of j. Now, just simply look into this particular scenario. I am going to explain over here. If S j and we are going to get some k such that phi is holds in this particular k. Okay. Now, what will happen if here I am writing that k is greater than equal to j. Okay. So, this is the time S j plus 1, like that we are coming to some state S k where time is progressing in this direction. So, if it is having k is greater than j. Now, what will happen if k equal to j? That means, if this is k equal to j means this particular state itself is your S j also. Okay. So, if k equal to j, I can say that this is equal to, just see in this particular case. Now, I am coming with a simple model. So, this is say S j and here say that in j itself phi holds. Okay. So, this is the scenario. I am just looking into one particular state S j, in this particular state S j phi holds. Now, if I am going to ask whether M S j in the state S j of the model M, whether it models f phi or not, or whether f phi is true in S j or not in this particular model. Just consider this particular model. Now, what is your view in this particular case? Whether this state S j, whether it models f phi, or whether f phi fuchsia phi is true in this particular state. So, if I look into the definition, formal definition, then what you will find that since here I am saying that k is greater than equal to j. So, that means I am coming to this particular scenario, that means in the state j itself phi is holds or phi is true, then I can say that in the state S j f phi is also true. So, if I say that whether this model, so according to our definition, yes, I can say that it is true or f phi is true in the state S j. Because why I am concluding like that? Because due to this greater than equal to j. So, if k is equal to j also in this particular case, I can say that yes, fuchsia phi holds in that particular state S j. So, what is the minor observation over here? That means, if I am in a particular state and phi is true and in next clock pulse, so basically what will happen? Already I said that digital system works on clock pulse. So, if I am having in this particular state S j, then next clock pulse as per the transition it will go to S j plus 1. Okay. So, now what we are saying according to the definition, if said that if phi is true in S j, then f phi is also true in S j. And why we are concluding it? Because this is as per the definition of this fuchsia operator. So, in this particular case what we said that we are going to capture the fuchsia behavior, but fuchsia is included in the present state itself. Okay. So, in this particular case I can say that the fuchsia behavior is included in the present behavior itself. But if I am going to write say instead of k is greater than equal to j, if we are going to write that k is greater than j, in that particular case what we are doing? We are excluding the fuchsia behavior from the present state. So, in that particular case if I say that k is greater than j, in that particular case in this particular state S j f phi will not be true. So, whatever semantics or meaning we are giving over here, basically future includes the present also. So, when we talk about the future behavior, that means presence is also included in the future behavior. So, that is why f phi future phi is true in S j if we are having such type of behavior. So, in the very next state say phi is false. Still f phi is true in S j because future includes the present. So, this is the notion of timing that we have incorporated while giving the meaning of those particular temporal operator. We can define the meaning of the temporal operator where we are going to exclude the present behavior from the future behavior. Then those definition will be slightly different, because instead of greater than equal to k, it will be only greater than k. So, in all those particular cases what will happen? We are saying it is greater than equal to k, that means future includes the present behavior also. But if we want to exclude it, then here we have to write greater than k. So, we have to be very careful while using those particular temporal operator, and the meaning truth values of the temporal operator will depends on the semantics that we are going to use. So, in our case basically we use this particular meaning that we will write k is greater than equal to z, that means we will say that future includes the present behavior also. Otherwise, the truth values will have some different effect. Okay. So, these are the, so similarly in case of future also, or in past logic also, that similarly that less than equal to k is coming to picture, that means past is included in the present, present is included the past also. Okay. So, that means what basically we can conclude here. Here I can say that if this is the timeline, and if I say that this is my present, and then here I am having future, and here I am having past. Now, how we are defining the semantic? future includes the present. That means, this is the future, it includes the present also. But if we want to exclude the present from the future, then what will happen? We have to start from somewhere here. Okay. So, accordingly, the truth values will be different in the present step. In this, whatever we have defined over here, we have defined with respect to this notion that future includes the present. Okay. Okay, this is the basic operators that we have in temporal logic, and temporal logic is can be categorized into two parts. One is your future temporal logic and second one is your past temporal logic. With the help of future temporal logic, we can reason about the system behavior in the future or for the future, how system is going to behave in futures. But if you want to know about its past execution, past behavior, then we can use the past temporal logic. Now, just after discussing of those particular temporal operators, just see some example how we are going to interpret it. Here I am giving one example, say P implies f of q. It is a temporal formula because say q is a formula and we can say that it is some propositional formula. Then f q is also a temporal formula, future q. P implies f q is also temporal formula, because I said that any logical connective can be used in the temporal logic. So, it says that if P is true in a state, then in a future state q is true. Okay. So, I am going to talk about the state. Say if I am going to consider this particular state as J, then what we are going to say that P is true at that particular point. And if I look into these things, you just see that if from S J you are starting in this particular way, somewhere in future we are going to get S k state where q is true. So, in this particular state I can say that f q is true. So, when I am going to look for this particular P implies f q. Now, whether this is true in S J, if P then f q. So, P is also true and f q is also true, that means in S J P implies f q is true, because in future we are going to get some state where q is true. Now, the next step is say S J plus 1, whether in S J plus 1, whether P implies f q true. Now, if I look into it in this particular state, from here in future somewhere I am getting a state S k where q is true. So, here f q is true. Okay. Now, here say P is not marked over here, that means P is false over here. So, whether now P implies f q is true at that particular state S j plus 1. Now, you just look into the notion of that implication operation. If P is true, then q must be true. This is the P implies q. If P is false, then whatever may be the truth values of your q, P implies q is true. So, since P is false at that particular point, so false implies anything is true. That means, P implies f q is also true in the state S j plus 1. So, like that we can see the truth values of a given temporal logic formula after knowing the truth values of each component. So, in this particular formula I am having two components, one is P, which is the atomic proposition, it can have truth values true and false, and f q is another temporal formula. So, P implies f q is a temporal formula. Now, it says that P or x q, either P holds in a state or in next state q holds. So, that means, if P is true in a particular state, then P or x q is true. So, since P is true at that particular point, so P or x q is true. Since P is true at that particular point, so P or x q is true. What about in this particular state? P is false. Since P is false, so second component need to be true. So, in this particular case, say in the S k q is true. So, in this particular state, that means x q is true, because in next state q is true. So, x q will be true over here. So, p or x q. If I look into it, then in this particular state p is false, but x q is true. So, p or s q is true at that particular state. Okay. So, again it is having two component x q and p, and they are disjuncted over here. Now, what about the next formula, p or q until r? So, whatever that I am writing p, q, r, you just think that these are the atomic proposition, they are having the truth values either true or false. If it is marked with p, that means it says that S 0 p is true, S j q is true, but it is not marked with p and r. You can say that this is your not of p and not of r. So, what does it means? Q is true in S j, but p is false and r is false. Similarly, if I look into S 0, p is true, but q is false and r is false over here. Now, we are talking about p or q until r. Now, whether in S 0 whether it is true, because p is true itself. So, it is immaterial of the other component. So, p or q until r is true over here. Now, when I talk about these particular things, S j, p is false at that particular point. So, q until r must be true over here. Now, you just see the execution that q remains true until r becomes true. So, here q until r is true. So, in this particular case p or q until r is true in that particular state. So, similarly, you can say that in this two state also p or q until r is true. What will happen to this particular state S k? Now, p is false. Now, we have to see what is the other component q until r. As per our notion of timing, we said that future includes the present state. Since r is true over here, so in this particular state p until q is also true. So, p is false, but q until r is true. So, p or q until r is true in this particular state S k. So, this is important. You have to see how we have captured time. Here we said that as per our semantic, future includes the present behavior. If we are going to exclude it, then this formula will be false in state S k. Okay. So, the notion is like that, whether future includes the present or future excludes presence. The semantics that we have defined over here is basically future include the present behavior also. Now, if I am going to have that, this is the similar way. Now, we can see whether p and q until r. So, q until r, one temporal logic formula, p is another one. So, now we have changed the label. So, what it says, in this three state p and q are true, but r is false in this three state. Here p and r is true, but q is false over here. So, here q is false. Now, you try to find out the states where p and q until r is true, and you try to find out what are the states that this is false. So, similarly, this is another example. Now, you try to analyze it. Here I am using the past temporal operator, where we are saying it is the previous. Okay. Now, you try to look for those particular states and say what is the truth values of this formula. Similarly, another question we are talking about, what does the temporal formula P implies that Q? Okay, diamond inside that Q. That means, this is basically not previous, basically back, actually in past. So, P holds in a state, then eventually in past Q holds. So, it is in past basically. Now, you try to give a define some model like that, whatever we are talking about, and label them with P and Q and try to find out the states where this particular formula is true. So, maybe you can use this particular model and label it and see whether the formula we are talking about P implies Q, this formula where it is true and where it is false. Now, another question I am giving, express the following information in temporal logic. P is true in next state or the next but one. That means, it is talking about either it will be true in this particular state. Okay. This is S0, S1 or S2. So, this is the behavior. That means, either P may be true over here or P may be true at that particular point. So, how I am going to describe this behavior in temporal logic? So, it says that in next state P holds or next to next state P holds. Okay. So, that means, this temporal operator can be again used. So, x p is a temporal formula. After knowing the truth value of x p, I can say x x p. Okay. So, this is a temporal logic formula. So, P is true in the next state and the next but one. So, this is the things. Consider fact P is an atomic proposition, write the temporal formula for P is infinitely often true. That means, wherever you go in future P is going to be true. Okay. Infinitely often. So, how I am going to capture it? Say this is infinitely often, say in future P, from wherever you go in future P is going to be true, and this property must hold globally. Okay. So, that is why G F P, it says that P is infinitely often true. So, globally this property must hold, wherever you go in future P must be true. So, like that, if we are going to have some notion, some specification where the timing is involved. So, such things can be captured with the help of this temporal logic, but remember all cannot be captured because we are having also restriction of this particular temporal logic operator. So, for that we may have to go for more operators. So, basically it talks about the expressive power of the temporal logic. So, we are having several notion or several behavior. Some of the behavior can be captured with the help of the temporal operators that we have discussed today. Okay, with this I am going to wind up today. So, in next class we are going to continue from this particular point. Thank you very much.